All right, welcome back. Let's talk about arrays through the lens of Big O, performance, and how do they compare to objects. Quick side note, if you've never seen arrays or you're not familiar with them, definitely go learn about them first. I'm not teaching them here. We're just talking about them and how they perform. All right, so the big selling point of arrays, of course, is that they are ordered. There is an intrinsic ordering to the data, unlike an object where things just float around in a gelatinous mass. And that's often very useful if we need order, but it can come at a cost for some of the operations. Anyway, here are two different arrays, of course. We can store whatever we want in there, different types of data, mix it up. And each element has an index, a numeric value that corresponds to it. So this is the 0th item, the first item, the second item. And in general, arrays, you use them when you need order. If you don't need order, then you probably don't want to use an array. If you're just trying to store random data together, you could still use an array, but if you're really trying to optimize for performance, there are other options. And even if you do need order, we're going to see some other structures coming up, like a singly linked list and a doubly linked list that still encode order. It's a list structure where each element is in a particular spot and they're all connected in an order, but they sometimes can perform better than arrays, depending on what you need. So arrays are not the only ordered data structure on Earth. They're just the only one that we get for free in JavaScript. Anyways, linked lists come later. So when you need an order, you can use an array, of course, but often that can come at a cost, depending on what you're trying to do, especially around insertion and removal. It can complicate things. So accessing data in an array is always very quick. So you can see here, access is O of 1, just the exact same as we talked about with an object. When I say access, what I mean is if we have this array with 3 items called names, if I ask for names of 0, or maybe that one's too easy because it's the first one. Let's say I ask for names of 2, it's constant time to give me Andrea. So a misconception that I've seen a lot of students have, when you have a 10,000 element array and you ask for the 9,000th element, let's say, JavaScript isn't going through every single element and counting all the way up to 9,000 and accessing every element and then getting to the one you need and giving it to you. You can think of there's a direct shortcut to each element. If you have a number, if you have an index and the array goes that far, of course, that's the one condition, it's a valid index, you can jump immediately to the data. So it doesn't matter how long the array is. It doesn't matter if you're looking at the last item, the middle item, or the first item. It's constant time. Okay, so now that that's out of the way, let's talk about insertion and removal. So it really depends on where we're inserting. Let's start with insertion. And it has to do with this order, as I've mentioned. Each element has an index that corresponds to it. And if I want to add something in, let's say I want to add in the name Raj. Well, if I add it to the very end, like right here, by pushing onto this array, that is constant time. It's O of 1. And that's because there's nothing difficult about that. We can add to the end of the array and we give it a new index. It's sort of like adding into an object. It's constant time. It's super simple. It doesn't require much work. The problem comes when we try and insert at the beginning of an array. And the reason for that has to do with these indices. If I tried to insert Raj here, you can already kind of see what happens. Our indices are totally messed up. Michael is no longer element 0. Melissa is not element 1. Andrea is not element 2. So we have to re-index every single element in the array. And this is simple for a 4-element array. But if we're talking about thousands and thousands of elements, re-indexing every single one is not a trivial task. So if we're inserting at the beginning of an array, we're talking about O of n time, because we have to do something once, roughly once, for every single element. Now that doesn't mean that it's exactly one operation for each element. Remember, O of n, it could be O of 10n, O of 2n, O of 0.5n. It's just that the amount of time it takes roughly grows in proportion with the size of the array, n. All right, so inserting at the beginning is problematic. The same goes for removing from the beginning. So if we do have Raj at the beginning, let's say this is our setup now. Oh, this is so annoying, having to type all of this like this. If we remove Raj like this, everything's wrong, right? We have to reindex again, just the other direction. We need to set Michael, its index, or his index is 1, Melissa goes down, 0, Melissa goes to 1, Andrea goes to 2. So you can see how this becomes difficult. Adding and removing from the beginning of an array is best to avoid if you can. But often it's meaningful to add to the beginning of an array. If you're trying to put something at the beginning of an order, for example, you may need to, so I'm not saying you should avoid it at all costs. It's just good to be aware that it's not as efficient as adding and removing at the end. So push and pop, always faster than shift and unshift. Unless, of course, it's an empty array, in which case adding to the beginning or end is the same thing. All right, so we talked about insertion and removal. It depends on where we're inserting. Always inserting, removing from the beginning is worse than adding to the end and removing from the end. Accessing is fast, no matter where. If we're talking about 10,000 elements, accessing the middle element is just as fast as accessing the second element. And then searching, the fastest we can do is O of n. We'll discuss this in the searching section. We'll write our own basic JavaScript search. If we're talking about an unsorted array, where there's no order to the data, if I wanted to know, if I had, let's say, another 10,000 names in here, and I wanted to know if Robbie was in there, we have to check potentially every single element. So as the number of items grows in that array, so does the time potentially that it takes to find that item. So search grows O of n, it's linear. And we spend a lot more time talking about search and potential optimizations you can make, specifically when your data is sorted, but that comes up later. All right, so next we'll talk about some built-in array methods and their performance, and then we're pretty much done.